Hello, everyone. So our speaker is Yongsun Kim. He earned his bachelor's degree in physics from the University of Illinois at Urbana-Champaign and his PhD in nuclear physics from MIT in 2013. After that, he worked as a postdoc at Cornell University and at the University of Illinois at Urbana-Champaign. Currently, he's an associate professor at Sejong University in Seoul since 2022. And he's now visiting Brookhaven National Lab. And he's going to talk about pentaquarks at the EIC.
But before he does, I'm going to embarrass him a little bit more. He's a proud daddy of 3 weeks.
Oh, thank you very much. Yeah. Thank you.
Where is your?
This girl, yeah, 2 girls now. Yeah, they're really in me in Vienna. That's why I actually drive late night today.
Wow.
Okay, thank you very much, and it's great honor to be here to give a talk. And this is my second visit in Yale University. The first one was about 2009 when one of my friends was doing his study here. And then again, I actually had some time to look around. I mean, walk around the city, and it was amazing. And also the museum was really amazing. So anyway, so when I got some suggestion from Jotan, when I got his email, so I almost right away answered that I'm gonna go. Yeah. Okay, and then so the topic for today is the opportunity of the Pentaquark measurement. This is a little bit different from what I have done so far, but I believe I found it very interesting recently. I really hope you also feel interested about this. Okay, so let me start my talk.
You have to click on that and then it goes.
Oh, okay.
And then, yeah.
There we go. So let me introduce myself.
If you go to the 3 dots where it says more,
On the very right side. Yeah.
and then you could do hide floating.
That one.
Yeah, this one.
Yeah.
Okay. I feel like I became my grandfather. One by one, please do.
Yeah.
It's not extra complicated. So
Okay.
we've all been together.
So yeah, as introduced by Johan, I have a background in Sejong University in Seoul. So he said it from 2022. So then I became the associate professor in 2022. So I came back to Korea in 2018, and then this year is my 7th year. So I used my sabbatical year at BNM. So that is how I easily came here. So I'm working on many experiments. So one is like CMS experiment at the 1 TeV, order 1 TeV, and I'm also working for the S physics, and also in STAR, and that is about 100 GeV. And also I'm also working for some much lower energy experiment, which is using the rare isotope beam. And the experiment's name is LAMS. It's like large arm on hadron with a multipurpose spectrometer at round. So round is the name of the accelerator in Korea, which was built last year. Okay, and this is some TPC that I'm making for the experiment in Korea. Okay, so that's mostly about me. And let me introduce my group at the university. So Sejong University is located in the eastern Seoul over here. Okay, and it's pretty close to the downtown. And one of I think the greatest the best feature of the benefit is that just across the street there's a really huge zoo. So if you want, you can actually just stop by and walk around and see some elephants, walking around there. Okay, so that was really the biggest the best part, the favorite part I really like. And the school is really a little bit small, but the physics department is relatively larger than other universities. And that is my favorite element. Sometimes they have some problems, so they actually break out the zoo. and then go inside of the restaurant and then break everything. Like sometimes that happens, okay? And that was I think like 2018 or something. And last year the Zebra actually ran out. And then I was sitting in my lab and I got some, the SMS, a message from the university that, okay, so one Zebra is running in the campus. Please do not come out with your building. Okay. So so that's what was shown in the news. Yeah. Anyways, I really like this campus. Right. Okay, and then let me introduce my the high energy and nuclear physics group. So we have four faculties, including me. So one is Yongsun Kim. That guy is working on the Pentaquark and the CMS high energy physics. And the second one is Sejong Kim. He's a theorist and working on the lattice QCD, so lattice gauge theory. And the third one is Yongsun. Oh, okay, there was a typo on my name. Okay, I just wrote it like just before this stuff. Yeah, I'm working on the experiment. And the last one is Hans. So I believe most of you. I think you were his advisor. Yes. Yeah. So he was the Yale alumnus, and we recently hired him. Literally, I hired him 3 years ago, and he's doing a great job. And so, yeah, this is how the formation of our group. And as I said, we are working on the various the energy the scales of energy, and we are working. I'm working with CMS, and Hans is working for the ALIX experiment. We also do some the star and recap and the spinning experiment, and at the very lower energy, like 10 GeV to 10 MeV to 100 MeV. We study for some how the nuclei are formed inside the star at the how are the nuclei are formed inside the star. Okay. All right, but today I will talk about a little bit different. So this is really even a new topic even to me. So the talk will be based on the two papers that I recently published with my theoretical colleagues. So one is a production of a PC 4312 in stating and the second one is the similar one but in the PS, which is the pentaquark form the hypothetical pentaquark formed with the proton and the phi mentioned. Okay, so I should start by praising the discovery of the LHCb. So you guys are undergraduate students, right? Or graduate students? Or even younger, high school. High school? Okay. I believe you guys heard of the LHC, right? Okay.
Probably not.
Okay. So, this is a really large accelerator. So that's all I can explain. Okay. And then there's where the Higgs boson was discovered. I believe you must know Higgs boson, right? Okay, not? All right. But anyway, so the most important discovery from the LHC must be Higgs boson. But I think for me, personally, the most striking discovery one of the most striking discovery of the LHC was very many new hadrons that was found from the LHCb. So you can see the new hadrons that was discovered in LHCb as a function of time. So for the last 15 or 16 years, there were 75 new hadrons found at the LHCb. Most of them are actually the Plutonian state or Plutonia or the new hadrons in the excited state. However, very interesting is I found the discovery of the Pentaquark, which is made of the 5 quarks. So the one is the PC. The PC is formed with the uudcc-bar. So UUD is a proton and CC-bar is a J size. So this is the decay channel they discovered with the LHC. And a little bit later, they also found the PCS. That is a UUS and CC-bar. So the D quark was replaced by this strange quark. So this is really, and there was, you know, the UUS is the lambda, and the cis-bar is again the J sign. So these are really, really very interesting discovery, which was made about five years ago. Actually, the first discovery was done in 2015, but it was updated later on. Okay, so this is the invariantness distribution of the PC brothers. So you can see the PC of 4312. So 4312 is the mass in the scale of MEV. And then you can see the peak around 4440 and 4457. So you can see the very clear peak, which is so obvious that the existence is so obvious. And then later on, they also found some of the tetraquark state, which is made of the 4 quarks, and which is called the TCC. So yeah, around 2019, the series of very interesting features were released from the LHC. So the LHCb, they discovered PC, and they discovered tetraquark and pentaquark after the first hypothesis rate of like 50 years, almost 50 years ago. And the CMS, they also found the enhancement of the X3872. So many interesting research. And actually, I expect some new research from Alice, hopefully from Alice. It will be really nice to see some TCC from Alice. So TCC is the tetraquark, is the UU-bar and CC-bar. And that might be highly enhanced, like the strangeness enhancement in heavy ion collision. So if you can find some very enhancement in heavy ion collision, that will be really striking research. But the problem, I actually tried to find it from the CMS, but the CMS, they don't have any PID. So it's really impossible to measure like K pi K pi K. So the combination of the 5 particles without the PID is also almost impossible. But I think at least is a really best place to study this. Okay, so the PC, they was measured by the LCB through the J psi and the proton decay. And as you can from this peak, this peak is really, really narrow. And I was really surprised the resolution of the LCB. So that the resolution was so good, so they were able to measure the width of each resonance. And you can see the PC, the width is 9.8 MeV, and their uncertainty is about 30 to 40% of the 50% level. But this is pretty precise. And that was really interesting finding thing I found, and that became the basis of my calculation. Okay, and before moving on, let me introduce. There was some bizarre history of the Pentaquark function. The story begins like about 22 years ago, 2003. So new state named the Beta Plus was claimed to be found at the lab experiment, which is I think was from the Jefferson lab. And they declared that they found a pentaquark state for the UUD and DS-bar. So this is kind of penta with a very light sectors. The mass was about the 1.5 GeV. However, many other experiments tried to cross-check, but nobody succeeded it. So only this experiment were able to see that, and there was no actually general agreement that there was actually the existence. So this is really in the middle of the controversy. However, but after the 15 years later, or 12 years later, LHCb found the pentaquark, the heavy quark sector made of the C port and C bar. And as I showed before, the peak was really clear, and that is, I think, should be the first evident discovery of the pentaquark. And the LHCb also found the PCS, as I said, that is made of UUD and CS-bar, or UUS and CC-bar. And many theorists says that maybe the pentaquarks, the 5 quark states are stable only when they have at least one heavy quark or one charm or a strange quark. So some diversity makes the quark system stable, like our society. I think this analysis is really interesting. Okay, so even though the pentaquark was already found, it's still it's still a really big question. So what is the internal structure or what is the quantum number of them? So the question, the biggest question is that, if the 5 quarks are inside of the same room, would it be, are they going to make some, some small the compact system where the 5 quarks are flying on the floating freely, or maybe 2 of them are merging or making a cluster, 2 are making a cluster, and the other 2 are making another cluster, meaning there's some kind of a molecular states. So that is one of the big questions. And another question is, what's the spin and what is the parity? So if this is a stable particle, they must have a well-defined spin and parity. And this is a question that I want to answer. And then to answer this, first, you have to really make a lot of them. So LACP is not really the best place because there are many underlying background and they are underlying background. So what would be the best machine to shed light on it? As my title says, the answer is EIC, but let me tell you why EIC is the best place. So PC was, we already saw that PC was decayed into JSON and proton, which means that we can actually merge create PC out of by merging JSON and proton. So the homework is, how can we grab the PC? The proton is really easy. There are so many protons in this room. However, creating grabbing JSON is really hard. But we know that the JSON is a CC-bar state. So occasionally it can convert into photon, right? So if you can, the shed literally shed light on the proton, you can make PC. But you need a very, very high energy photon. And that can be delivered by the branch problem of the electron. Okay? So if you collide electron and proton, you can actually form some Feynman diagrams that can make PC like this. Okay? So I was actually I was playing when I saw the news about the PC from NCD, I was drawing this Feynman diagram on my desk, and I just brought it to some of my theory colleagues in Korea, in the Yonsei University. That is a western part of Seoul. It's about 1 hour by drive. And then there's a guy, this professor named Soo-Hong Lee, and he showed a big interest and told me that it's really possible to make PC from this channel. And as you see, we need electron beam and proton beam, and that can be delivered by EIC in the really near future. Okay, and if ever it is made, then this will be the event. The particle we will see is made of the PC. So the proton and electron collide, and the electrons will be scattered off after giving the photon, and the PC will decay into proton and J side, and which will be decayed again into electron and plasma. So this is really clean event with almost zero background. Okay, so this is a science mission which is written in the webpage, also in the long range plan. And the science missions is a precision 3D imaging of the proton and the proton tomography, and the solving the proton spin puzzle, and the confinement and PDF modification in nuclei. But I'm trying to convince people that maybe the exotic hadron and the discovery and the characterization of the Pentaquark can be really another mission for the EIC. So many people I believe the people are actually overlooking this potential. Or this is only my propaganda. All right. So okay, how can we make the PC? So this is the Feynman diagram in the particle level. Okay, so first of all, actually, I showed this to Professor Lee in Yonsei University, and I asked him, can you calculate what is the cross section for this process? And he told me that okay, this is too complicated, but you can actually simplify that diagram into this in the hadron level. So in this diagram, there is no quark. This is just hadron, and this is what physicists done in 1960s before the discovery of the quark. They were actually really dealing with the interaction between the hadron and hadron. There's no quark, and they were really successful in doing this by modeling the interaction. And then, I think the people in the 1960s were so clever that they managed to, to avoid, they're thinking about the problem, but they try to, precisely calculate the cross-section on this. And one of them is the vector-meson dominance phenomenology. So which means that photon has a spin 1 and charge equals 0. And the vector-meson, they are also at the spin 1. So the wave functions are overlapping each other. So there is some non-zero possibility that photons are converted into the J side, the vector-meson. And obviously there must be the virtual photon. Okay. So if you can calculate the probability that photons are converted to J side, then we can do some calculations. Okay. And then the second thing is that you need to know what is the interaction strength or the vertex between J side, proton, and PC. So because you need to make some Lagrangian. And this one, we know we can calculate, we know that LHCb already measured the decay rate, which means that you can calculate back the vertex strength of this vertex. Then you have everything on your hand to calculate this. Okay, so let me elaborate a little bit more about the vector-meson dominance. So in this Lagrangian is the J side to gamma. So Lagrangian. Okay, let me skip it. It takes a little, a week to explain it. But anyway, you just need this equation to calculate the probability that the photon converts to J side. And this is really the elementary calculation that you can learn from the quantum field theory in the first year graduate school. And the second one is that what you need to do is you calculate the second one. And there is one the free parameter. The free parameter can be actually calculated back from very well-known decay of the J side into E plus and E minus. So actually, vector-meson dominance was used to explain the decay of the rho measure of the E plus and E minus, the E plus and E minus. And you can do the same thing for the J side and to calculate back this one. So you know that the decay rate of the J side is 92.9 keV, and the branching ratio is 5.9%. And then you can calculate the free parameter in this model. So that is fixed. The second is you have to calculate the vertex strength between proton, J side, and the PC. And for this, we made four different scenarios. The first one is a spin half or spin 3 half. And the second one is a parity plus and parity minus. So depending on what kind of quantum number, the strength will be different and the Lagrangian will be different. Okay. And we just use for the spin half, you can use the Dirac equation, and spin 3 half, you can use the Larita-Schrödinger equation. And those the Lagrangians are very well known, and you can do the calculation very easily with the mathematics. Okay, and then by plotting in the decay width of the PC, and the branching ratio to J side to proton is about 3%. That is actually purely a theoretical calculation, but I think it's pretty decent the proposition. And then you can actually calculate back you can calculate the interaction strength, which is a GJPPC, and in 4 different scenarios. Now we have everything on your hand to calculate the cross section. Okay, one more. So this is just in the propagator based on this. So, the propagator 1 over Q square minus M square, something like that. Okay. So now, if you measure it, then you need some apparatus to measure it, and that is that might be the EPIC can be the first detector which can measure it. So if this is the recent illustration of the EPIC detector, and apparently it can measure the charged particles with a very high efficiency and with a wide coverage of the pseudo rapidity. And the pseudo rapidity coverage is more like the plus minus 3.2. But when we did study this study, it was like 3 years ago. So we just used the ±4. Okay. All right, and this is the result. So this is the cross section as a function of the speed rapidity. And right hand side is a cross function as a function of PT. And then this is the expected number of the PC which can be produced from the EIC based on the 10 inverse femtobarn. So 10 inverse femtobarn is the expected the integrated luminosity if you take the data for 1 month, 1 month. But actually there was a really peak luminosity, but the table actually evolves, and the peak energy is actually the energy, the luminosity goes down by 1 order of magnitude. So, but luckily the paper was published before that. So anyway, so you need 1 year to get this number in this table. So depending on the parity and the speed, we can collect 1,000 to 10,000 of the PC. So this is huge actually, and this is really a number of the PCs. There was a PC accumulated from the LHCb for several years. So I think the EIC is a really powerful machine to measure the Pentaquark. Okay, and the yields can be even enhanced for the lower collision energy if we actually approaches to the threshold of the PC mass, or if the PC has a spin of 3/2. If the PC has a spin of 5/2, then this statement is wrong. And we are actually doing some the follow study with the 5/2 scenario. Okay, and that's not all. Another benefit of the EIC is that it's the ability to polarize the beams. And this is some outdated the table from the trick page, but the polarization says that we can 80% of the electron can be polarized and the 70% of the proton can be polarized. And this is really, really strong the big benefit which already the star of the Phoenix experiment is getting. And this is really important to pin down the quantum numbers of PC. And let me show you that. So so this is an epic coverage of plus minus 4, and then this is a rapidity distribution of the PC. And this is the result when the beam is not polarized. Sorry, the beam is polarized already. Okay, so there are 2 things. So first of all, when the beams are the polarization is parallel, and it means that the left-hand side and the right-hand side, then sorry, that was the anti-parallelized. Okay, so left-handed and right-handed collide, the cross-section will be looking like this, and the left-hand side and left-hand side and right-hand side, then cross-section will be looking like this. Okay, and then you can see that they were almost same. However, they are beginning to diverge in the forward region. Actually, this is the different convention from the usual EIC. So this is electron going and this is proton going. Okay. However, if the spin is 3/2, then they show the same qualitative the divergence, but the divergence happens much earlier when the rapidity is around -2 in the proton going. So, that kind of, 2 different behavior from this, we can actually say that if the PC is spin-half or 3/2. So, so we can quantify this difference by defining the beam, the BSA, which means the represent for the beam symmetry. I forgot. I actually the beam BSA. So one of them should be symmetry. Yeah, beam spin or symmetry. Sorry about that. Beam spin or symmetry. And this is quite a common variable for the spin polarized beams. And so basically, what it says is the difference between the 2 cross sections for the different polarization divided by the sum of them. So if this is 1, so if it's 0, then the cross sections are exactly same for the left hand, the same hand digits and different hand digits. And if it is 1, then the production happens only the one hand digits. Okay. And for spin half, the BSA goes rising around 2, but the spin 3 half and it begins to rise into -2. So by using the benefit of the epic, meaning the wide rapidity range with the chromatic coverages, we will be very clearly see that if whether the PC which has a spin 3 half or the 1.1 half.
What is the dashed line?
Oh, dashed line is for different parity.
Okay,
For spin half, 3 half, there's no dependence of parity, but spin 1 half, yeah.
okay, thank you.
That's it. Okay, then what about the parity? What about the parity? So if the spin if the spin is 3 half, then we cannot really resolve the parity and use the BSA. And even in the spin 1 half, the difference is almost only 20%. 20% is really some bizarre number for the experimentalists. It's really hard to draw. And typical systematic uncertainty at the LHC is around the 10%. So 20% is quite some bad number. So we need some better observable to resolve it. So one thing we can do is the polarization of the J side decay. So it's basically like the PC decay, but let me explain what it means. So J side are polarized. So it has spin it's not polarized, but it has spin 1. So it has some so you can so the decay the decay angle means that angle between the decayed muon or electron with the J side momentum. The distribution is different for the transverse J side and the longitudinal J side. So we can actually tag we can tag the transverse J side, for example, by selecting only the J side that is decayed into this direction. Then, for example, if you select this one, then we know that the most of them are the transverse. And if you select this one, then the majority of the longitudinal, but some 20% are some mixture between 2 to 3 of the longitudinal and transverse. Okay. So now after tagging this, you can check the polarization between the PC and J side. So because the cross section to produce the transverse the cross section to produce the transverse J side out of PC, that depends on the parity of the PC. So by checking the decay angle between the PC and the transverse J side, and we can actually resolve on we can actually the distribution of the cross section is different for the positive parity and the negative parity. This is not really 100% difference, but still it's better than the PSA variable. So the summary is that by using the spin polarized beam at the EIC, you can not only produce a lot of the Pentaquark, but measure the spin and the parity. Okay, and some question that I heard from
Before you move on from that one.
Sure.
So, but you need to measure the angle between the J side and the PC. Isn't this very short lived? Can you actually resolve?
Oh yeah, because we fully reconstruct the PC. So we know the momentum of the PC.
Okay, yep.
Yes.
Does this include, I guess I don't know if this makes sense, but does it include both coherent and incoherent production?
So this is so I know the word question, so there's the photo production, but this is really this is P plus E. So it's really in terms of P, it will be like coherent production, because the production is made by just exciting you just excite the proton and then convert the proton into C.
Right.
Yeah.
So, but you don't want the case where the proton would break up. So
this is EP collision. Oh, sorry. Now I understand your question. So that's not really built with this model. So this model really think of the proton as just a single particle.
Okay, but then I guess when we have the measurement, those would be the background that need to be removed in order to compare with the.
Yeah, that's
calculation.
right, yeah, background. However, in that case, the multiplicity will be much higher than this process, so we can easily move that out. So if the proton is, yeah,
So like you would have a jet and then once
no
you.
jet.
Yeah, I mean, you would have a jet in that case and then you would reject
right,
that
yeah,
event.
yeah.
Okay,
Yeah, the event is really clean, so this is how it look like. So electron, proton coming in, and PC and electron coming out. No background,
okay,
yeah,
yeah.
if the assumption is correct.
Hmm.
Okay. And so now let me move on with some other experiments. So after showing this research in some conferences, I was heard of some question that why wasn't it this observed in JLab experiments? So JLab they did the gamma the collision of the photon and the electron, and essentially same to the EIC, and I found out that the answer is follows. So first of all, the luminosity the luminosity itself is higher than EIC. However, the luminosity to produce a photon, high energy photon, high enough to produce a pentaquark is lower than EIC. And in the GLUX experiment, what they're doing is that they make they accelerate the electron beam, and then they use the photon that is radiating from the electron. So they are 100% real photon. However, in the EAC, we can also use a virtual photon, which also enhance the probability to the cross section to produce the pentaquarks. And the second thing is that so this is a result from GLUX, and this is not really invariant mass of the PC. So this is some paper that they showed their attempt to measure the PC. What they show is the inclusive cross section of the J side. So they actually checked they drew the J side cross section and said that if the PC if the PC 43 12 was produced, they should make some peak around here. So I don't know exactly what is the problem, but they didn't use the proton to fully reconstruct the invariant mass. But they actually at least they used the proton to tag the event. So they actually use the proton for the event as the trigger and the event selection. So again, so another benefit we can see from the EPIC is that the detector is really good. So we can produce a lot of we can fully reconstruct the pentaquark. Okay. How many minutes do I have now? Okay, okay, and more recently, I did a similar study on the strangeness of the sector. So by replacing the charm quark to the strange quark, we can also think about the production of the uudss-bar, which is named as PS. And there were many theoretical studies to calculate the mass of PS. And there are some in the hadron physics community. There is some agreement that the PS should have mass around 2.071 GeV, and so I met one of the people in hadron physics conference, and we wrote a paper together, and which was published this year, and yeah, so this is what it is. But the result is really similar, and we try to fit our calculation in the existing data. We actually used some data which was published in the 1973, 82, 79, 80, 89, very old, and three of them was made before I was born. Yeah, and then but really couldn't resolve. And then the conclusion is that we need EIC to really clearly say that whether or not the PC exists. Okay, and this is some another variable, the spin density metric component. This is really the proxy of the spin polarization. But but mostly used for the low energy vision. Okay, I think we can just skip it. All right. So for the rest of my time, I'd like to show how the PC will be look like at the EPI. So after I came in BNA, I spent some of my time to simulate the PC 4312 using the EPIC simulation. I think the name of the simulation was DD-HEP, and that was really nice. And what was really impressive is that it ran out of box. You know, usually they don't run out of box. But I think people in the EPIC is working really well. So yeah. I answered some questions to the ChatGPT, but still work very well. So let me show you. Okay. So as I said, so most of the pentaquarks are produced in the fourth division, because as I said, you know, the working mechanism like the proton and electron comes like here. The electron shoots some the photon, and photon actually excite the proton and converts proton into PC. So PCs are more likely to be produced in the proton work direction. Okay, and those can be detected by the forward perimeter. The forward detector system in the EPI, so which is a tracker made of the ACL dot and the double reach of the chunk of mirror and the forward colorimeter around there. So they are covering the rapidity between 2 to 4. And then we can also think of the very powerful detectors. So those detectors will be installed about 40 meters, between the 20-40 meters away from the interaction point. And these are composed of a B0 detector, and the Raman pump, and the GEC. So they can measure the protons and neutrons. And the PC are decayed into protons, so we can actually grab measure the protons from the PC using this powerful detection. Right, and so this is a result of the simulation and the rapidity distribution. You can see the left-hand side. The distribution of the proton and the electrons in the forward detector, and there is some the particles reconstructing the far forward, and there is some gap between the two detecting systems. And the right-hand side is the momentum resolution. So as a function of momentum. Actually, this is not really there is some bias on here, because this is really the two parts 2-to-2 interaction. So once the PT is fixed, then rapidity is automatically fixed. So this is not only the momentum dependence, but the rapidity dependence. But anyway, the momentum resolution is between the 3 to 15%, which is not really bad. So with this, this is a reconstruction efficiency. That actually includes the acceptance. I was a little bit surprised that the acceptance efficiency is pretty high, around 90%. Okay, so this is efficiency for the proton and electrons in PC. I think this is only for the proton. And sorry, but really the PC. So which means that all three particles are the reconstructed in the detecting system. And the right-hand side is the efficiency for the J side to the E plus and E minus, and then they are pretty high. And with this, you can draw the inherent mass distribution of the PC, and you can see the peak around here. And the width was measured to be around 160 MeV. So okay. Compared to the LHCb, this is not really good. So we may not be able to see resolve the piece, the three different states of the PC. However, if he just the pin down, if he fix the mass of the J side with the PDGID value, then we can actually make a narrower the peak of the PC, and this is commonly used in the trick used for the LHC and other experiments. So in that case, the best resolution will be 40 MeV. So 40 MeV means that we cannot resolve these two, but however, we can resolve the ground state and second and the third state. So yeah, this is the performance performance of it. All right, so let me move on to the summary. So not this one. Why? Okay, this is really summary. Sorry about that. There's some I don't know why that is actually came in. Okay, so many hadrons were discovered over the last decade, and the perspective of the hadrons is evolving very rapidly. I think this is really interesting. And the EIC can be the powerful machine to produce and study the pentaquark, in particular the heavy pentaquark, which is made of proton plus QQ-bar. Okay. And we suggested that the vector-meson dominance model says that there will be plenty of pentaquarks can be produced from the EIC. And the high energy and the luminosity and the spin polarization are the great deal of benefit for the precision measurement of pentaquark at the EIC. Okay? And the last message is that we should seriously consider it as one of the EIC nations. Thank you.
For this excellent talk, it's time for questions. Perhaps I can start with a question. What if you consider pions, for example, maybe in a different model, and to study tetraquarks, for example?
Oh, tetraquarks.
So you have your J star, but instead of the proton, you consider pion.
I mean, okay, that question is, I believe it will be possible inside of jet, maybe. The problem is that, we have to, the benefit of the EIC is that we are using the proton beam. So proton beam can be the seed for the PC. But for the tetraquark, we actually put the pion and the CC bar into the same space. So maybe some jet can be some place for that. But if that is true, the LHCC experiment must see that as well.
Yeah, okay. More questions?
So about the APEX simulation, can you go to the slide where you showing the this one? So, I mean, currently, I guess you don't have the background included.
For this, yeah, there's no background.
Right, which will significantly reduce your efficiency. They have a huge background, right?
Well, actually,
The beam rest.
but that can be actually reduced from the trigger level probably.
Right.
And one different thing from what I found very interesting from the EIC experiment is that particle multiplicity is really small for EIC. There are at most 7 particles in the experiment. So yeah, the effect of background is really small. But
But the beam induced background is huge.
that will be huge, but that is not counted in the luminosity.
Right, but
Why would that make a background here?
but in the sense like your resolving power for electron. You have synchrotron photon decaying into E plus E minus.
But beam background cannot make J side.
But not jet side, but you can do it electron.
Yeah, but he's making the E plus E minus turn into a J psi.
But you are measuring jet side by E plus E minus. Right?
Yeah, but then, so there's a background to the J psi, and then I guess
Yeah.
you might say, and now you've got to reconstruct the correct invariant mass.
Right. I mean, you will have some fundamental.
Yeah. There must be some background for the E plus and E minus, but I think that can be easily removed by invariant mass window.
Are they going in the same direction? No, because you're.
Oh, yeah, right. That's another thing. Yeah, different direction.
The
Yeah.
PC is going
The
the
P
other
going
way,
direction.
right? Because it's going in the proton direction. Am I thinking about it wrong?
Yes, it is.
Okay, and then isn't the electron from the beam going the other way?
No, I mean, I'm talking about the electron beam interacting with the beam gas.
Mhm.
And producing that background. And that background is following.
That must be, that must be boosted in the electron going.
Yeah.
Right?
Yeah, so that will be in the electron going direction, but the PC is made in the proton going direction. I think this is really good.
Well, but synchrotron is all. But another thing is, so you could tag the proton, right?
Yes.
From the current simulations. Is the current DB4 have set up?
Yeah.
And this identification is coming from which detector?
Okay.
Yeah, but like PID.
Actually, for this, I didn't use any PID. Actually, yeah.
Team-rich direction.
I just assigned the proton mass and electron. So actually, basically, we can do that. But for some personal reason, not really related to collaboration, I just try to see what will be the background if I could mismatch the proton and electron. The effect was really, really small.
Right.
Yeah.
And my impression was they haven't implemented yet the PID detector.
Yeah, there are many PIDs. Yeah.
Yeah, but they're not implemented yet. Before.
In DD4, they are partially implemented.
That's what I mean.
Yeah.
So,
There is some problem in the technique, in the software. That's why I didn't use it.
right.
Yeah.
But it would have been identified with D-rich, right?
Yeah, enrich, yeah. Oh, yeah. For both proton and electron. Also,
Okay.
so let me finish it. So also we are thinking of some people are working on the muon identification for epi without muon R. I don't know if that is possible, but if we can manage to use muon, then we can actually double the statistics.
Wait, how?
So because the J psi can also decay into
Oh,
mu plus
okay,
mu
I
minus.
see.
Yeah. Yes.
So this was great. I actually have a question about something that you suggested that you were looking into in terms of figuring out what the spin of this object would be. Because you have the curves in which you show, I guess, the decoupling between the two, comparing 1/2, 3/2,
Yeah,
and then one of them has a neat sort of thing, and then the other one doesn't.
This one, that one, yeah.
But I guess it was the other plot that you had with the comparison of the spin before the BSA. Yeah, this guy, these two.
Yeah.
Yeah. So I'm curious as to, for the 5/2,
Yeah,
which sort of substructure would those curves have?
that's a really, really good question. So 5/2, their structure is exactly the same to 3/2. Because the Lagrangian is really similar.
Sure.
Yeah. The gamma 5, the position of gamma 5 is different for 3/2 and 5/2.
Okay,
Yeah.
same structure, but different position in the.
Yeah,
in the
yeah.
axis.
The overall average is different. However, the ratio is exactly the same.
Okay.
Yeah.
Very cool.
So we have an unusually younger audience here. You must have some questions. You came here for a reason, I guess. No stupid question.
Smart.
That's not. What did you hear about the talk? Sorry. No, but for real. What did you hear about the talk?
She was asking how to, about this talk, be able to attend.
You guys are very welcome.
Yeah, I'm just curious.
I'm also very curious.
We just come from China, and all of the students come to attend a college visit tour, and then all of them plan to apply the US college in the future. And today we visit Yale, but we happen to know there is a seminar. I would like our students to feel what is the college seminar looks like.
Yeah.
So
And the students' backgrounds are in science.
most of
or-
them are very interested in science.
I see.
And especially for boys, they like physics, math, and chemistry. So that's why I think that will give them the first class to learn universities to like.
That's nice Olympiad guys. So we are talking about the future experiment, which will be done in like 10 years. So I think they're really perfect timing for you guys.
You heard it first.
Not high school, but I do have a question.
Is, do you have PC production with electron-ion collisions?
So, yeah, so I should give a middle school answer. So, yeah, it should be possible. So if the vector-meson dominance works, then there should be also produced there, produced inside of the ion.
Yeah.
but will be processed inside a cold nucleus.
Mm.
So it will be really interesting to see the interaction with it. Actually, you know what? I started this study to measure it at the LHC in the UPC channel. So when I brought, I actually drew the Feynman diagram in the UPC channel and then brought this to, the theory guy and said, the energy is so high. So the energy is so high, so they cannot really, the virtuality of the photon cannot be really good enough to make the PC. So we actually, so I was a little bit disappointed, but found out that the EIC is a perfect place to measure it. Yeah. But again, your E plus and EIN will be really interesting as well. And another thing, let me add one more thing is that, so the PC, the production can also really highly depends on the center of mass energy. So if the spin is 3½ then it will really will increase if you lower down the energy near the threshold. But if it is the spin is 5½ it will really increase as a function of the CO center of mass energy because there is more kind of in the space, so the momentum space that it can be formed. So I believe some kind of beam energy scan at the EIC will be really interesting in terms of this. So I show that the PC can be produced at EIC, which means that PB like proton and BD bar, that can be also produced by the same region. So there, if that works, then EIC can be really the Pentaquark factory.
I was going to ask you, could you put up the LHC Pentaquark states, the 75 or so, to the slide? I was going to ask you about
Which one?
PB.
Oh, PB.
Yeah.
This one. So PB is not observed yet.
I know that. That's why I want this. Now, is LHCb, first of all, is there enough luminosity and energy, and are they really looking for states with beauty?
I'm not sure. I don't know if anybody's working on that, but I actually read some random theory papers about the PB cross section, but it's really, really small. So out of run 4 and run 5, there are less than handful PB is produced at the LHC. Because they are measuring the PC or whatever that is the fed down from the lambda C. The PB should be coming from lambda B, I believe.
Yeah.
So you said it only has a very small branching ratio to this, and very naively, I would have thought it was higher. So what does it decay in? You said it was 3% into it.
Yeah, 20%, something like that.
But wouldn't that depend on what a pentaquark is?
Yeah, exactly. Yeah, that is why. So that is why, not really, but the region and the research is actually swapped. The reason why they think of the decay branching ratio to the proton and J psi is that majority is that they think of the pentaquark as a molecular state of the D and lambda C. The reason is that this is the inversion mass, and this is the mass of the summation of the mass of the the sigma C and the D bar, which means that their mass is slightly below the sum of the sigma and D, which means that it might be some molecular state of those two particles. So the majority will be decayed into there, and only 3% will decay into the P and J side. So in our calculation, we already accounted the low, the branching ratio, but still there are many.
Already, well, we have to go. We
Sure.
have a next activity. Thank you very much.
Thank you. I thought like next concepts are coming every seminar. So I like, wow, this seminar is really diverse.
Yeah, I do.
These are not paid actors.
Any more questions? If no, then let's thank the speaker again.